Good afternoon.
Hello.
All right. All right, I want to keep you awake. So I'm going to talk about the digital twin as it's driving 21st century transformation, because I think it's probably one of the biggest things that we've got going. There's a lot of technologies that are coming on stream, digital twin, IoT, AI, machine learning. I think they all sort of are converging to allow us to do things that we really couldn't do in the past. And so I'm going to give you sort of a selected brief overview of what the digital twin is, how it impacts. I'm going to kind of focus on manufacturing. I'm going to finish off talking about additive manufacturing because I think that's also a technology that digital twins could basically make for production capabilities. So So this is the original digital twin, and it was developed when I was here 20 years ago. This is the second time I publicly talked about it, and it was at the Lurie Engineering Center when we were setting up a thing called the Product Lifecycle Management Development Consortium. And it was the second time because the first one that generally gets cited was at an SME conference in Troy, Michigan, in October, but this was in December 2002. And so the model hasn't changed that much. It had a different name at that time. We called it the information mirroring model. Wasn't a great name. It wasn't until my colleague at NASA, where I was been a consultant for over a dozen and a half years, focused on the fact that it was called the digital twin. So he actually named it. I give him credit in my book, Virtually Perfect, that came out in 2010, and I switched to using that name exclusively from that point on. But it has pretty much the same conceptual componentry as it does today. Probably the difference is that I kind of highlighted this idea of having virtual spaces to do things with, and what's my problem? Virtual spaces to work with. And at that point in time, that was kind of a new idea. So I've since subsequently dropped that because I think that's now an assumption that everybody understands. But this was the original idea for product lifecycle management. It was underlying premise, and product lifecycle management and digital twins are interrelated throughout the history. PLM came about at that time period in the early 2000s. And so this was the underlying premise for how you could control products from their inception through their disposal. So this is the digital twin model as today. It's got better graphics, courtesy of NASA, hence the rocket ships and rocket engines and things like that. But there are sort of three main components to the digital twin that have to exist. On the left side is the physical space, and so the physical environment and the physical products that we've always had. And so since time immemorial, this is the space that we were relegated to deal with. On the right side is this idea of the virtual space and virtual representation, not only of the products itself, but of the environment. So we need to have the environment that is the same environment as a physical space. So, I mean, you're hearing things about metaverse and things like that. I mean, the issue of it is that it has to, the virtual space has to fully represent to the right granular perspective the actual physical space. So you have to have the same rules and things, and we're getting better there, but we're not there. But some of the issues I've seen with metaverses is we really don't have to follow all the rules of the physical space. And from my contention, that's never going to work for what we want to do here in the digital twin. So the third thing is that we have the connection between the two spaces. So we move data from the physical space to the virtual space, and then we use that information in the physical space that we've created in that virtual space. And so this is basically the concept of the digital twin model. And I'll talk about the different types of digital twins in a second. But if you think about the model in this particular perspective, I think that that'll help you understand. Now, people talk about, well, what's the definition of the digital twin? And I am not fond of definitions because I think that from a conceptual standpoint, complex concepts don't have a very good idea of definitions. Definitions only work if you kind of know what it is. The example I use is the blind men and the elephant, where depending on what part of the elephant they come across, one comes across the tusk and thinks it's a spear. The one comes across the tail and thinks it's a rope, and the guy on the side thinks it's a wall. And so you know, if you start to look at definitions, you wind up describing part of the elephant here, and I think it doesn't do good. So the last time I looked, there were like 400,000 different definitions of digital twin out there. So I am not a fan of definitions. I actually have one in the first chapter that I did, but I think that you have to think about it in terms of models. I mean, the picture is worth 1,000 words. Well, in this particular case, it certainly is that kind of capability. And so why do we want to do this? I mean, we want to do it because of the fact that we want to move work activity that we've done in the physical world from the 20th century and since time immemorial. We want to move that into the 21st century. We want to move as much of that work we can into the virtual world. And so our focus is using this information to be much more effective, efficient, and even innovative than we have in the past. So I want to spend a minute or two talking about why do we want to do this? And so if you look at information, in my perspective, that it is a substitute for task wasted time, energy, and material. So physical things. So much of, if not most of human life, is this idea that says that our task is a goal-seeking activity with minimum physical resources. What nature does is it tries all possible combinations and let the environment sort it out. We can't afford to do that. So we want to minimize the amount of resources that we do for a task. And for any task, I can divide it up into two pieces. The green piece there is the most efficient and effective way we possibly could do that task. So if we were omniscient and omnipotent, which we clearly are not, then we would only use the physical resources that it took to do the task in the minimum amount possible. So whether it is, you know, manufacturing a product, developing a product, or even getting 3 kids to their practices after school, we would want to do that in the most effective and efficient way possible. Anything above that is what I call information inefficiencies. We've wasted time, energy, and material. Because we live in a capitalistic society, we can cost that out. So we can cost the different units of time, energy, and material in order to be able to understand what the cost of doing it this way is. And so what's sort of interesting is we actually have a name for this in manufacturing. It's called lean manufacturing. The intent of lean manufacturing is to use a minimum amount of physical resources in order to produce products. So we've always had this kind of concept, but we haven't been able to really articulate why that is. Because quite frankly, there are not good definitions for information. We wrap ourselves around the axle trying to define information. And the reality is we want to know what information does. This is an ideal, and I'll explain, but information is a replacement, not for the physical resources that we need to do the task, but for the information inefficiencies. Now I'm showing the ideal situation where we replace all of information inefficiency. That's never going to happen. But the takeaway from this is the fact that the information doesn't replace the physical resources we need to do. They're the same in both bars. The issue of it is that it can replace information inefficiencies. So what we're looking at is using information to replace wasted physical resources. Well, the problem we have with information is, what's a unit of information? I mean, a wit instead of a bit? No, nobody knows. There isn't an ability to define that. But we can get to a proxy, and the proxy is hardware, software, people's time. And so we can cost that out a lot tougher than maybe how we've done it before. but we can approximately get that cost out. So how does this work? When does it work? It only works when the cost of information is less than the cost of wasting resources. And for repeatable tasks, that is a pretty good idea. For those of us who have made our money in the computer business, that formula luckily has worked for us. So the cost of information and developing information has gone down exponentially, and the cost of physical resources goes up. So even if it was even today, I'd want to basically create information rather than wasting, than using physical resources, because the information costs are going to go down exponentially, while the cost of wasting resources is going to go up in the cost of inflation. And we know what the cost of inflation is doing today. So this is the underlying premise of why we want to use the digital twin and how we can basically get value out of the digital twin. If I can get value out of this, they're pretty pictures. So what I want to do is to think about where can I basically replace wasted time, energy, and material when I'm doing the task, no matter what kind of task it is. So just to kind of reiterate that, this is the graph of Moore's law. Now, you're all familiar with Moore's law, right? Okay. And so we started about here in 1970, and it's not, quite frankly, not a law, it's a prediction. But we passed, in fact, about 80 billion transistors on a chip just recently. And my projections are that it's going to be 7 trillion or 128 times increase by 2030, and approximately 885 trillion transistors on a chip or equivalent at 16,000 times increase. And this is without quantum computing, which I don't know whether we can really solve the error correction problem, but I think you're going to see some special purpose quantum computing coming on stream in the not too distant future. To give you an idea of kind of that, I was, in fact, I was responsible for the first supercomputer called the Iliac 4, which was in the 1970s. We had 25 megaflops of capability, and it filled up the atrium easily here, okay? Today, if you've got an Xbox, it's about 12 teraflops, trillion teraflops, and the box is obviously very small. So you can see the immense amount of capability that we already have, but quite frankly, these are big numbers about what we're going to have. So digital transformation is clearly going to take place given the kind of capabilities that we've got coming on stream. So the digital twin model, in terms of scope and scale, initially it was for the aerospace and automotive business, but I'm seeing digital twins for pretty much everything. If you can imagine it and it's tangible, you can have a digital twin for it. So automobiles, locomotives, power generation, airplanes, ships, oil rigs, oil and gas industry is really big in this particular thing. And even over the lower corner, I'm seeing, digital twins of people. So not only for healthcare equipment, but also for patients themselves. Quite frankly, if you think about it, digital twin of a patient is how many of you walked into a doctor's office and filled out the 30-second time the form that they asked you to do that, okay? It'd be great to have digital twins of people so that we didn't have to do that. Big area is digital twins of the building and cities, so smart cities, smart buildings. We saw the use of digital twins not only in the vaccine development business for COVID, but also in the ability to treat it. I'm seeing articles on digital twins of the Earth. I got to tell you, I don't think we're there yet, no matter what they're claiming. It's an interesting article about the digital twins of the ocean. But my point is that pretty much anything that was tangible, you're going to see digital twins for. Now, I want to make the point that you need to drive this from use cases. So I want digital twins of some of the complicated things or complex systems, aircraft, spacecraft, oil rigs and things like that. I don't need a digital twin of a paperclip. So you need to drive this from use cases because it goes back to my value proposition that says that we're replacing wasted information. I might say. The other thing is that you're going to hear, and I'm not a big fan of this, but this connection is often called the digital thread. I've hung on throughout my career by a thread too often to be very comfortable with that. I'd like it to be digital pipe or a digital beam, but digital thread is the idea that we're going to connect these two areas together. We're starting to even see the scope and scale in intangible things. So logistics, the process industry, we're going to see it in even economic systems, manufacturing processes, and if you look at this came out from ASME, supply chains, being able to have digital twins of your supply chain to know where your product is at all times and what the condition of it is. So it is not simply relegated to tangible items. We're starting to see it for intangible. So my premise is that if you can imagine it, you can basically create a digital twin of that kind of capability. And so I think the sky's the limit here in terms of if you're involved in digital twins, you can basically be in any kind of industry and have a digital twin be that kind of capability. So what I do is I divide digital twins into types. Remember, the whole idea of this was to have a premise that underlines the entire product life cycle, right? So one of the big problems that we've had in the past, in fact, still continue to do so today, is the fact that we siloed information. Information was in the engineering, and then they threw it over the wall to poor manufacturing guys and said, go build it. And you know, that had major effects in terms of going back and forth because they couldn't. And then the poor support people who had to maintain this stuff, you know, had no idea of what the design intent was, how it was built. So we at the same time this was going on, or the reason was we were moving from a functional centric world where every discipline had its own information system to a product centric world. And so the whole idea was to basically have this idea of a product centric view and have the digital twin exist across the entire product life cycle. So the first thing we have in terms of types is what I call the digital twin prototype, or the prototypical digital twin. These are all the products that can be made. So this is the product and its variants. And notice that it starts very fuzzy as an idea, and at the end, you basically, it is a fully formed product that I actually can build. And so in fact, ideally, what I'd like to do is I'd like to do all my work in this particular area in the virtual world. I really would like to do, ideally, is to design my product virtually, test my product virtually, manufacture my product virtually, support my product virtually, and only when I got it all right do I basically want to go out and actually move around expensive physical items. So we clearly aren't there yet, but that's sort of the goal. In fact, that's there's an article on the World Economic Forum where my colleague at NASA says that that's what we'd like to do. And especially in things that are very expensive like NASA or aircraft carriers or nuclear reactors, oops is a very bad word. So you want to make all your mistakes in the virtual world as opposed to do that. So these are all the products that can be made. When I start to make products, I want to make what I call a digital twin instance. And that is the actual replication of the product that is physical products is going to exist. So this is where and this is kind of where it gets confusing for some people because they basically think that's the only digital twin there is, but it's not. But this digital twin is really important because I basically want to create the digital twin instance of the specific physical product and link to that product throughout the rest of its entire life. And so up here, I have a design that has, say, specifications that have variances in it. When I get to this point in time, I actually have a number of what I've made. I actually have a part number of the individual parts. So I want to create what's called the as-built and basically have that so I can connect that through for the rest of the time the product exists. So these are the individual products that are made. Finally, I have a thing what I call the digital twin aggregate. And this is really the power of digital twins, is if I can basically take all these digital twins together and collect information on it, I can, in essence, then do prognostics or predictions of how those products are going to perform. So I want to create the digital twin aggregates of all the products that have been made. And that's going to allow me to in essence, have a window on the future that I'm going to talk about in a few minutes. So this is sort of the focus of the digital twin. So digital twins, it isn't just simply a digital twin. It has different types depending on where you are in the life cycle of the product. And by the way, the digital twin instance is going to use a lot of this information, if I do this right, from the digital twin prototype, because I need that information and I don't need to recreate it. You know, the issue with physical products is they're an all nothing proposition. I either have that airplane or I don't have that airplane. With the digital twin, I can have information granularity and I can have pieces of that information of what I'm interested in. I can have the skin of that airplane or the propulsion system without having to have the entire airplane. So this opens up a whole opportunity for us to do, in essence, a better job of being able to not only design the product, but also maintain the product, not only the as-built, but the as-maintained. So here's the digital twin throughout the product lifecycle, because quite frankly, you can't just focus on your area of the product. So you can't focus on, I'm an engineer, I don't really care how it's manufactured or how it's supported. And so we need to use this information in order to develop and maintain this product throughout its entire life. So the first thing in the creation phase, and I just talked about that, is we start off with the basic model. However, we also need to have the means of production. If we have simply the designs, you know, we have pretty pictures. We do not have the ability of how I can manufacture that. In fact, the design in fact, I got an argument with the CEO of PGC who said, you know, manufacturing is a function of engineering. And I said, wrong. It's engineering is a function of manufacturing. I basically try to manufacture the product to basically create my virtual design. And so the means of production, how I actually go about creating this is the key to being able to have a product or simply a fantasy of something that I thought I want to make. So I use this is the create phase, and I use the digital twin prototype at this particular point. This is sort of the most complicated point in time in the build side, is that not only do I have my digital twins of my products, and I want to, in essence, create the digital twin instance of the product I'm making, but I also have to feed the information to the machines that are making that. And the virtual machines need to tell the physical machines what to do, and I need to monitor that so that I can actually create the physical version. Remember, physical reality trumps virtual reality every day of the week. So I've got to basically be able to create my physical product. Once I do that, I then can create the digital twin instance of that product. So I use the digital twin prototype, the prototypical digital twin, and then I get the digital twin instance that I'm going to connect to that product throughout its entire life. When I get to the sustain or operate phase, I basically then have my physical product and my virtual product, and I collect information from my physical product to my virtual product, and then I use that information to do good things like, you know, fix things before the problem occurs. And so in the sustain phase, I use the prototypical digital twin, the digital twin instance of that thing, and then, as I said, if I have an aggregate of that and I can have good information about cause and effect, then I can basically create that product and do a good job. One of the things I'm sort of fond of saying is that a frequent flyer, you do not want an engine failure at 30,000 feet. I don't even want an engine failure when I'm sitting in the departure lounge, because that means I'm in for a long delay. What I'd really like to do is to predict that whatever that component is going to fail, and then be able to fix it the next time through the maintenance hub and never have the problem exist. The last piece of this, and this piece has been missing for a long, long time, is a connection between the sustain phase back into the design people. And too often I've seen generation after generation of having the same problem that gets fixed. And the reason is that nobody's told the design people it just doesn't work that way. And so the digital twin allows us to connect that information back and feed it back in so that the next generation of the product fixes that particular problem. So the manufacturing piece of this has different names today. You know, it's Industry 4.0, and I don't have time to talk about Industry 4.0 has kind of adopted this because they were sort of on the wrong path. Smart manufacturing, industrial Internet of Things. So you may have run or should have run across this sort of descriptions, you know, as you've gone about working in this particular area. And so this is all sort of related to how we're doing that stuff. So the digital twin instance model, and I created this back in 2008, is this idea that says, look, we want to measure the physical data in the manufacturing process. We want to collect and organize that data. We want to create the as-builts, because if we don't have a baseline of what we've created, it's going to be very difficult to have an as-maintained. And then we want to present the as-builts to the real world, the physical world, so that we can do that job. So I just want to spend a few minutes talking about a common fallacy that has been out there for a while. It's getting much better, but the fallacy is that the digital twin requires a physical counterpart. So I'm part of AIAA, and unfortunately they put out a really bad paper that basically said you don't have a digital twin until a tail number rolls off the factory. And that's just wrong, because it has a lot of problems. And as I said to the director of AIA, we're going to burn that bridge when we come to it. But it's a fallacy that I just want to run. The twin metaphor has duality and similarity. It's not timeline similarity. I mean, too often people think of human twins and they both come out at the same time, okay? I mean, the twin metaphor is I simply have to have duality, this looks like that, and then I have to have some similarity that they both exist at the same time. And so they don't have to exist simultaneously. So I have a digital twin well before I have anything physical if I've done this right. The digital twin framework should cover the entire product, as this shows. So I shouldn't just start it when I manufacture the product and the product rolls off the assembly line. Even the people that are telling me this, the digital twin actually exists. They just call it a different name. The manufacturing system model or the development system model, and it's not semantics. How we talk about things is how we think about them. So this is just not a semantics problem. It is basically an idea that says we're trying to regress to being functionally siloed. And again, I hope I made that point, but we really don't want to do that. And then I think it's just conceptually inelegant and piecemeal. If our premise is that it's about the whole product life cycle and not about any particular part, then we really want to have a concept that covers all those particular pieces. So here's how the digital twin kind of works in time. So if I look at the fact of a physical timeline, and I'm at a time of 0 plus X. So I'm not at time 0, I'm somewhere out, okay? And then I'm looking at time X plus Y. What do I really want to have here? And what I want to have is this idea of replication, which was one of my first papers in manufacturing, is I would ideally like to have the replication in the digital twin of what's going on with the physical world. And why? Because it doesn't matter where I am in the world. I mean, instantaneously and simultaneously, people can basically have the information. In manufacturing plants, there's a reason why they put the foreman's office over the factory floor, so he could look out and see, he or she could look and see what was going on. The digital twin allows anybody anywhere with the right security to know what's going on with not only the product, but in this particular case, the factory machines that are occurring. So factory replication is really a key thing of what we want as a minimum for digital twins in a factory situation. But there's this thing what I call front-running simulation. And if we do this right, we can predict the future. It can be our crystal ball into the future of being able to predict to us what's going to occur at some time X plus Y. And so it may not be able to predict, you know, perfectly because we don't live in a deterministic world. In fact, it won't be able to predict perfectly, but it could give us probabilities of things that are happening. So if I have a glitch in a robot, I would like to predict that in X amount of hours, I'm going to have a bottleneck, and I want to go fix that bottleneck before it occurs. So this idea of front-running simulation is that every time zero, I run a new simulation with the data. It has to have the data that I have at the exact time, and then I use that with my digital twin aggregates to predict the future. And so the ability of being able to do that is why the digital twin, sometimes I say, is a time machine. It allows us to look into the future to determine what's going to happen. So my prediction is that not only on the factory floor, but products are going to have front-running simulation running in every product to predict and help us be able to do a better job. So the digital twin is going to say, hey, stupid, don't be doing what you're doing, because in the next, you're in an automobile, in the next 10 minutes, you're going to wind up crashing. So you really want to be able to predict the future here with respect to that. So this is sort of the idea that we have that says the digital twin is good about replication. We want to replicate what's occurring with its digital twin instance, but then we want to predict into the future. This is going to be where the real power of the digital twin is, to allow us to replace wasted resources. So how are we doing in this evolution of the digital twin? I mean, what's going on here and where are we at? And so if I look at the physical to virtual maturity, moving work into the virtual world from the physical world, and then I look at the information evolution, how good our information is being able to deal with this, it looks like this. This is a traditional way where we basically have blueprints, and then we wound up creating prototypes and parts and determining whether or not we could make that happen. So it's at level zero. I mean, this is what we've done since time immemorial. I mean, the big opportunity here is when we created blueprints in the mid 1800s. And in fact, before the middle of the 1800s, we couldn't have interchangeable parts because there was no standard for measurement, no standard inch, and no standard way of measuring. The Pratt & Whitney machine tool company created that. In fact, they created the National Bureau of Standards by addressing that particular problem. At that point in time, everything up to then was a one-off custom piece, and you couldn't have interchangeable. So what was the first mass-produced thing we did when we could figure out how to do that? Come on, you're U of M. Somebody needs to give me an answer.
Firearms.
You got it. Guns. So the first thing they did, and that's why in West Hartford you have the firearm companies, Smith & Wesson and Colt, that were located next door to Pratt & Whitney machine tool company. Transitional. So I mean, this is relatively recent. This millennium is that we started to move from the physical stuff into the virtual stuff, and so the big deal here was when we moved from 2D drawings to three-dimensional objects, and that occurred in the early 2000s with the CAD/CAM people. Remember, CAD stands for computer-aided design, so it was not about developing models; it was about helping a draftsman be able to get that. So in the early 2000s, we basically transitioned from flat land, if you will, to the three-dimensional land. Where I think we are right now is the conceptual basis. So we are all conceptually understanding what the digital twin is in some fashion, but we have to pull a lot of the information together on an ad hoc basis. In fact, I saw a great application of this for ADNOC. I think it's Qatar's energy. So they have a digital twin of their oil fields, their pipelines, their refineries, and I'm in the position of basically saying, is that a video or is that a model and simulation? I mean, it was that good. And they have a wall that basically shows all that across their entire infrastructure, and they've saved $1 billion. They've probably spent about $100 million developing it. When we get to, we're starting to see platforms. So ability of being able to have a platform where you can create a digital twin, and we're going to get to replication doing that. And then finally, what I call front-running simulation or intelligent digital twin, an intelligent digital twin platform that will actually help predict the future, and it will predict different states and give us probabilities of those states so that we can look at how we're going to be able to handle our products and be able to prevent failures from occurring. I mentioned Industry 4.0. Industry 4.0 started off with a premise that said, you know, what my goal is to reduce the time from a fault to remediation. And I critiqued that and said, you know what, I really don't want to have the fault occur at all. So you're starting to see Industry 4.0 saying we want to prevent this by using digital twins. So reducing the time of a fault to remediation is good, but if you never have the fault, it's even better, and it'll save you massive amounts of money. So I'm going to talk for a few minutes about, in fact, this is my latest paper. It's available out there on ResearchGate and on the Digital Twin Journal. But the idea of digital twins versus intelligent digital twins. So the digital twin is pretty much passive. We basically have to go out and work with it. The intelligent digital twin will be active. It will be constantly looking at the environment and the issue, and it will basically work that. The digital twin is pretty much offline today. We're going to have that in constant contact. We give the goal for the digital twin of today. Intelligent digital twin with AI will be goal syncing and minimizing resources. So while the digital twin could be predictive if we ask it the right questions, the intelligent digital twin will be anticipatory. I mean, it will basically be a little agent sitting on our shoulder saying, hey, you need to consider this. My perspective of AI is not that it's a replacement of humans. We have plenty of humans. We don't need a replacement. But it's going to be an ability to help humans make better decisions throughout their time. And so we're starting to see, you know, AI machine learning come into play here to help us have more intelligent digital twins. So I'm going to spend the last few minutes talking about, you know, digital twins and additive manufacturing, because as I said, you know, the idea that what we really want to do is to design the product virtually, test the product virtually, manufacture the product virtually, support the product virtually, and then go out and move expensive atoms was a premise. I would really like to print that. So we're going to get to the point where we're going to print it. In fact, I promised the Navy that in 2075 they can print an aircraft carrier. They're not happy, they can come find me. But I think that additive manufacturing is the ability to bring manufacturing back into the United States. And so I think this is a real focus that we need to have. So this is the additive manufacturing framework. In fact, it was developed by Dr. Susan Smith, and I helped a little bit. And it's in a how do we make better decisions in 3D technology and 3dprint.com. But it's the idea that says we're going to have size, accuracy, material issues, and then cost and throughput. So can I build it is the big question for additive manufacturing. And then the next is, should I build it? So, I mean, one of the issues is I can additively manufacture an engine block. It only costs me about $20,000. I can cast one for $500. So even though I can do it, I ought not to do it. So this is sort of the underlying premise for additive manufacturing. You know, size, accuracy, material, can I build it? And then the economics of should I build it? And so if I look at the current additive problem of manufacturing risk versus cost hierarchy in manufacturing, it looks like this. The least cost, but the highest risk is the product shows up and I simply accept it, okay? Shows up on my loading dock, first time I've seen it, and I just put it into production. That's low cost, but it's high risk. The next is certification. I've gone through some certification process that I basically told my customer that I'm going to do, and so they were relying on the fact that I have certified it in some fashion. I can do inspection. I can do samples, or I can do 100% inspection. So less cost, less risk, higher cost. And then finally, testing. Testing is a very, very expensive process here. And so I can either test a sample or test 100%. In fact, the only way I really know if the product is going to perform the way it is to test it to destruction. Unfortunately, I can't sell a whole lot of those, okay? It's a way of making scrap. But that really is the only way I really have it said, this will handle X amount of hours of stress, at this kind of stress level. What's interesting is that information, if I had that information, as I showed early on, is that it is probably the least cost and the least risk. So if I could able to predict the future about this stuff, that the information about that is priceless. I mean, I lower my cost and I lower my risk. Today in additive manufacturing, we almost we pretty much do 100% inspections. So expensive. So turbine blades, GE's making turbine blades, they have to CT scan every single turbine blade to understand that. So they're making additive manufacturing and then they scan the blade itself. My claim is that if we could basically be able to use a digital twin, we can do something that we haven't been able to do today. So there's this thing that in fact I've worked with Oak Ridge National Labs on called Digital Twin Certified. And that is, we have to capture sufficient process production data of AM parts. So remember, additive manufacturing is about creating melt pools and having those melt pools be homogeneous enough that they create I'm not talking metal specifically here, but it's plastics and anything else, that they have the sufficient capabilities that a steel mill produced part is. I want to create a digital twin instance of that part. So if I can collect enough of what they call voxels, I can understand what those sorts of things are. And then I can test a digital twin to destruction. It doesn't cost me anything to do that. And we're seeing that in aerospace and in automotive. Automotive crash tests are very expensive. Okay, with a digital twin, I mean, with a physical one, I can only do certain orientations because it's just a very expensive test to run. With a digital twin, I can do it at every orientation on the compass and find out that I have a crumple zone that doesn't show up except in an oblique crash. In aerospace, one of the tests for aerospace is you bend the wings of an airplane until they break. That's expensive, okay? For the airplane, and the testing is expensive. Today, and they used to go through 2, 3, maybe 4 airplanes to get one that met the requirements. Today, they do one. So we're getting to the point where we're testing virtually and then validating physically. And I will sort of contend that we don't even have to look at the physical validation if we've done this right. In fact, Ford Motor Company in my book, Virtually Perfect, I talk about the fact that Ford has decided in some tests that the tests are really not representative enough of the product, and so virtual testing is superior to that. So this came out of a workshop at Oak Ridge National Labs, and in fact, they picked up the digital twin certified additive manufacturing. These are research areas which I think are going to be extremely important. So additive manufacturing parts have processes that are not identical and have variances from part to part. The current AM inspection process are time consuming and cost prohibitive for most parts. So we just talked about that. Virtual AI analysis and testing of real part geometry to destruction would enable additive manufacturing uses. And then overcoming, so this is not a technical problem, it's a cultural problem, and it's huge. So is that cultural initiative and establishing trust is the big part. So convincing the testing people that we can test virtually. So what's the state of the art? That the part qualification certification are a major expense and impediment to AM adoption. So how we do it today is just too expensive for production. That we basically use fairly large grain data tracking, so Traveler forms, CT scanning and other non-destructive tests, and a prohibitive amount of coupon testing using AM for only non-critical parts. So their airline industry does some stuff with non-important bulkheads and things like that, but they can't do it for airworthy parts. how to determine and train on massive amounts of data, determining what characteristics need to be censored, cultural initiatives in the testing community, and label data. So how do we know, and that's a big one. So what's interoperability of data? We're still wrestling that big problem. In fact, interoperability of digital twins is a huge, huge issue that I don't have time to talk about today, but I've spent a lot of time discussing that's our issue today, and how do we address it? And so what are the research opportunities? So this is where you guys come in. So censoring AM in process produced data AI can use for prediction, collecting the data while you build it for buildup of DT. There's a paper out of Vanderbilt that just came out a few weeks ago that starts to address this problem. It was a pretty good paper. Real-time control and defect healing, AI analysis of test to destruction to determine fidelity with physical testing. Again, physical world trumps the virtual world. So it doesn't do me any good to do the test on the virtual part if it doesn't reflect what the actual physical part is. But if you look at some of the things coming out, it's pretty good. I mean, I saw crumple zones, for example, on a car, and you can't tell which was the photograph and which was the modeling simulation. Combining ML defects detection and physical modeling for prediction part failure, especially for low volume parts. And then material properties. So we've done the genomic of materials, we need to incorporate that. So if we can do that, we'll enable better design for additive manufacturing. So additive manufacturing designs, there's all kinds of opportunities there I don't have time to talk about, but we can do much better designs with better functionality, lower part costs if we could do additive manufacturing. So we help engineers design better parts that are optimized for AM processing. Manufacture qualified small to medium volume parts for regulation intensive industries, and then enable all the promises of additive manufacturing. So additive manufacturing has been around for a long time, but to get it to production is going to require what we're doing now. So I'm just going to spend the last 4 minutes talking about digital twin impediments. So these are the problems that we're facing here. So height potential. People are saying, oh yeah, I can do everything with digital twins. Give me $100 million and I'll give you that. As a former CEO, I can tell you, you'd last in my office about 2 minutes, maybe less if you did that, okay? You gotta go find the right projects. And again, it's gotta be driven by use cases. The ability to have a fully formed virtual world where your parts are of unbelievable granularity is not gonna be very useful if I don't have use cases that create value. Organizational culture and initiative. So just the fact that, in fact, and this is a big problem in major corporations because the people that are in charge are the people nearest to retirement. So they've got retirementitis. Oh, please don't do this because this got risk. And so I don't want to get fired before I retire if this doesn't work. It's got to be driven by use cases. So what's my value proposition? Where do I get value out of trading off wasted resources for information? Lack of cohesion and integration, I could talk about that for a whole hour, but the whole ability of the fact that you have cohesion in the physical world simply because atoms force you to do that. You got to program all your cohesion into the virtual world. And so then integrating different digital twins, so if I have different digital twins of machines on the machine floor, they better all have equivalent capabilities that I can get to. And then finally, my big one is cybersecurity. So we open up a whole can of worms in terms of security when we start to have a digital twin out there that if I have a physical thing, I can protect it behind fences and walls and armed guards. Cybersecurity is a huge, huge problem because it now becomes available. So here are selected publications of mine that talk about different things. As I said, the last one just came out a couple of weeks ago, Intelligent Digital Twins and the Development and Management of Complex Systems. So one of the areas I'm interested in is complex systems which have real different capabilities. And in fact, when you throw AI into the mix, they have emergent behavior, which is going to have to, if we put autonomous vehicles out there with AI, we better have digital twins on Overwatch capability, or else you can bet that there'll be cascading and catastrophic failures of those things if we can't get in control of them. So with that, I'll entertain any questions.
Thank you very much for a great talk. We do have time for some questions here in the room, and I think Mickey's going to monitor the chat on Zoom. So if you have a question, please raise your hand. Yeah, go ahead.
So you mentioned earlier that some validation now, not just verification, but validation is starting to be done using digital twins. What sorts of requirements with regard to like fidelity of simulation in the virtual space would be required to do more of this validation, most if not all of the validation?
So the number one requirement is the fact that your digital twin is an exact replication of the physical world. Okay, so once I have that, then I can run. So I run through the design space and check all the possible combinations to see if that occurs. I can't do that physically because that would require, you know, gazillion parts. But you know, if I use the Taguchi box, I mean, there are ways that I could basically convince you that this part has the same fidelity. But the big problem is going to be cultural, convincing folks that if they don't do 10,000 coupons, and by the way, if you think about it, doing coupons and then saying, well, this part that I made, you know, is reflective of that. Yes, there is. I worked in the steel mill. Yes, there is homogeneous capabilities of steel, but it's not perfect, you know. I mean, and so I think that it's really a cultural problem of getting the testing folks. Now, the good news is I think digital natives, you know, you guys are coming into the workforce to basically who understand this. This is not an age thing per se, but you know, you're going to find more people who are older who have to put their hands on it versus young people, and so we've got to get over that cultural inertia.
Not yet. Oh yeah, go ahead.
Yeah, so in the last slide, you were talking about digital twin in additive manufacturing.
Yes.
So I'm just curious whether the goal of this project or this type of work is also correct additive manufacturing process, or no, you just you understand the process, you understand what you are making, what you will make, but can you also correct the process? I mean,
good question. And so yeah, so the thing is that if it's an anomaly of the part, okay, then that's, you know, that's the thing of, you know, do I accept the part? Can I correct it? Whatever. But I know that it meets the requirements or doesn't. But you're right. If you start to see sort of a drift of over time, so it's a longitudinal thing that says I got a problem with my manufacturing process. So I hadn't thought about that, but yeah, it basically would also allow you to go back. And in the case of that, so this works for subtractive manufacturing, right? But in the case of additive manufacturing, it may be I have to adjust, say, the power of the lasers or the type of powder bed material I've got or whatever, because I'm getting inconsistent results. And so yeah, so it is an ability to handle both sides of that. I had pretty much thought of it about being able to certify the product as meeting the requirements, but yes, if you collected the data longitudinally, it would tell you whether it's like statistical process control. You know, is there, you know, when I plot this out, you know, do I have, you know, something within a range, or do I have outliers that make this a non-viable way of doing things? So good question.
Go ahead.
My questions.
Yeah, go ahead.
Not yet. Yeah. So similar with what we have in manufacturing maturity readiness level or technology readiness level, do you see that we are moving forward to have a similar scale for digital twins maturity level? And if so, where do you think we are between the scale between 1 and 9, for example, at MRL?
So technologically, I think we're at like 6 or 7, right? The problem is culturally, I think we're at a 2 or 3. Now, NASA is working on addressing that, but we have, my prediction is we're going to reach a tipping point here where people are going to start to get comfortable with this. But we're not there yet. I mean, there's still the testing and certification people are still very much in the physical world. And in fact, my colleague from NASA just did smart manufacturing, and his slides were, this is where we need to go. I mean, because we cannot afford. I mean, what's interesting is there are industries where we can't afford to do the physical thing. Nuclear power is one of them. We can't afford to build nuclear power plants of different variations and see if they work, okay? It just doesn't work. So what's interesting is that we tested nuclear weapons, you know, for the last 50 years, if you will. And yet, so nuclear power is one of those that they have to have that. Spacecraft is another one. I mean, it gets, you know, a launch is $500 million, you know, and up. So we have to be able to get those work. And NASA has done a good amount of work, although I have to say that, so I live in Cocoa Beach, I get to see all the launches, which is kind of cool. SpaceX has done a far better job, to be perfectly honest. Problem with NASA is everything's a science project, and they kind of miss, you know, where SpaceX is, yeah, we're just going to launch stuff, and they do a fairly good job. So I think that it's going to be slow until we reach the, you know, a punctuated equilibrium, and then people are going to say, why did we never do this stuff? Because I don't think that the technological piece, I mean, we do have some work to do, for example, in additive manufacturing, in getting the data from the parts, you know, what is the, what for a particular area, what is the melt pool, you know, size and shape and liquidity, okay? So we've got some work to do there, but that's you know, engineers are good at figuring that out. So we have some work to do there. And then I think the digital twin part of it, you know, FEA analysis, things like that. I mean, we can test the destruction today. I mean, that's not, I think, a huge problem. Maybe at the margins, we have to do, you know, some more work, but we pretty much understand a lot of that stuff. So I'm pretty bullish about that. We got to get over the cultural issue from my perspective. I mean, we got to be able to produce airworthy parts using this, or else we're sort of stuck in the physical world.